anyway, thank you very much for the invitation. So yes, today I'm going to talk about my recent work and also work in progress about Crosscap states and integrability. And it's mostly based on the work that I did last year with João Caetano, and also work in progress with João Caetano, who is a fellow at CERN, and Leonardo Rastelli in Stony Brook, and Paulo Soresina, who is a visiting student at CERN right now. And I should also mention that there are two interesting and important related works, one by Tamas Gambor and the other by Christopher Ekman, which are also about Crosscap states in spin chain. So let me begin. So before explaining the detail, let me just first explain what is the Crosscap, because the Crosscap states might not be so familiar to many of you. So the context in which the Crosscap states have been studied is actually in the context of 2D conformal field theory in the past. And in 2D conformal field theory, the Crosscap states are defined in the following way. So let's consider a 2D conformal field theory defined on R2, the flat infinite space, and then cut out a small disk. And then furthermore, you perform the identification where Z is going to be equal to -1 over Z bar. So you basically identify the points outside the unit circle and inside the unit circle. So after this identification, the fundamental domain after this identification can be taken to be just the exterior of this unit circle. And so this defines a non-orientable manifold or non-orientable surface, which is related to the so-called Crosscap. And more precisely, the Crosscap state is defined as a state which is obtained by this geometric manipulation. So let's consider the radial quantization of the 2D CFT starting from this origin. And then if you look at this complicated manifold, which involves identification from outside, then you can replace the effect of this identification with the insertion of some non-trivial state. And I should also mention that, as I said, this identification maps the point inside and the point outside to the point outside, but on the unit circle, it basically identifies the points which are antipodally separated. So the alternative way to construct a Crosscap state is to just cut out the disk and perform antipodal identification at the boundary of the disk. And the result of which, the result of that manipulation is called the Crosscap state. However, so this is studied a lot in the past in the 2D CFT, but I should mention that there is almost no work on massive theories, in particular massive integrable field theory, or or the integrable spin chain, and that is the subject of my talk, the main subject of my talk. So let me just give you the punchline of the talk. So the punchline is that the integrability survives in the presence of crosscaps. And the second important point is that the overlap between the Crosscap state and an excited state can be computed analytically, both in field theory and spin chains. And I'm going to present you the closed formula for that. And furthermore, in the application of ADS-CFT to the ADS-CFT correspondence, they compute 1-point functions in n equals 4 super-mils on what's called RP4 geometry, combined with what's called charge conjugation. I'm going to explain what I mean by these RP4 and charge conjugation later in the talk. Okay, so let's start. So this is the plan of the talk. So let me first explain to you why we care about crosscaps. So before I explain the reason why I care about the crosscap states, let me just explain the reason why I care about the boundaries, which are kind of like very much closely related to the crosscap states. So the boundaries and defects in 1+1 dimensional systems have attracted much attention in the past, both in condensed matter physics and also in high energy physics. And one of the most successful examples of the boundary in 1+1 dimensional system is what's called Condo Problem or Condo phenomena, which is basically some anomalous resistivity of certain metal observed in the experiment, which differ from the naive theoretical prediction at low temperature. And Kondo proposed that this anomalous increase of the resistivity could be understood as a result of magnetic impurity and propose a simple model which consists of free fermion and magnetic impurity. So this is, of course, like a 3+1 dimensional model because it is supposed to describe our real metal observed in an experiment. But if you take this model and just consider the S-wave scattering of the free fermion, then you can reduce this model to 1+1 dimensional fermion with a certain boundary condition. And what's remarkable about this system is that it can be actually solvable by using the method of integrability and also CFT. And I should also mention that what's called Kalan-Rubakov effect, studied in high energy physics, is also very much related. And if you do the dimensional reduction, often reduces to a similar kind of models. And another reason why boundaries are important is that if you consider two-dimensional conformal field theory with boundary, then we know that it describes D-branes in string theory, which is an important non-perturbative object in string theory. And more recently, people started using boundary states in conformal field theory or spin chains as the initial state of the quantum quench. So the reason why this is good is because boundary states is defined locally at a point by the boundary condition, and therefore it has a very, very short range entanglement. And therefore, if you use the boundary state as the initial state of the quantum quench, you can study, it is a basically ideal initial condition for studying the evolution of entanglement. And more recently, the boundaries in 1+1 dimensional spin chain and integrable field theory found application to n=4 theory, for example, in the context of defect one-point function or determinant three-point functions. In two-dimensional conformal field series, there exists another important class of states that is precisely the crosscap states. And these crosscap states are important also in the context of two-dimensional systems on non-orientable surfaces, and also 2+1 dimensional symmetry-protected topological phase with time reversal symmetry. And in addition, in the context of string theory, it is important for studying what's called orientifold. And basically, the orientifold is defined as something that corresponds to crosscap on the worldsheet. And the one important and strange feature of the orientifold is that orientifold can have actually negative tension, unlike the D-brane, which can only have positive tension. And this feature is very important in various string phenomenology and string compactifications, in particular for the construction of DS vacua. And however, as I said in the beginning, there is almost no literature for integrable for crosscap states in integrable field series and spin chain. And as we will see, the crosscap states in spin chain provide new integrable initial states for quantum quench, which are long-range entangled and exhibit volume law for the entanglement. And furthermore, the analysis in n=4 suggests a new class of defects in general higher dimensional conformal field series, which I would call orientifold defects. So those are the motivations. And is there any questions so far? Okay, so if not, yes.
Hey, Shota. This is Lance.
Yes.
You mentioned the Condo problem, but this is a higher codimension defect than the Condo problem, if I understand it right. The one.
Yes, Condo problem is originally like essentially codimension 3 defects in 1+3 dimensional system.
Yeah.
However, in the actual analysis, people often do the S-wave reduction. So people consider the scattering problem. And if you do the S-wave reduction, and then you can reduce it to 1+1 dimensional system with a boundary.
But then it's codimension 1 in that problem, whereas yours is codimension 2, so more like an instanton than a particle defect or something. Is that right? Or am I getting that wrong?
From the worldsheet point of view, it's more like, so, okay, first of all, here I was just talking about the boundaries, and the boundaries is always codimension 1. And I would say Crosscap is also very similar because the special region in this picture is basically unit circle.
Okay,
so and the circle is
more as extended than as that point.
Yeah, it's more like extended.
Thanks.
Yeah. Okay, so let's move on to the actual computation. So now I'm going to explain to you how to compute the cross-cap overlap in integrable field series. So to compute the cross-cap overlap in integrable field series, we consider the following setup. So we consider the cylinder with circumference L and the length R, and we contract the two endpoints of the cylinder with the cross-cap states. So topologically, this actually corresponds to what's called Klein bottle, although it might not be obvious. And my goal is to analyze the partition function of this Klein bottle in two different expansions. So the first expansion is what's called tree-channel expansion, which you can obtain by inserting a resolution of identity here. And if you do so, then you get this following expansion. So you have the overlap between some energy eigenstate times cross-cap state square here and here, and then you have some propagation factor coming from the state propagating for a distance r. And in particular, if you take the large R limit, then you can project this sum to the contribution to the ground state, because the ground state has the lowest energy. And therefore, you can compute the cross-cap overlap by first computing the Klein bottle partition function and taking the limit where R goes to infinity. So this is the tree-channel expansion. So what's more complicated is what's called the loop channel expansion, in which I regard this L as a time direction. So in this expansion, let's consider some like a time slice, which I denoted by red line. So in this context, the time slice is a little bit complicated, because if you start from here and like extend the space direction to here, then because of the antipodal identification, you need to continue this space direction here. And then after coming back here, you can, after going here, you can come back here, which basically means that constant time slice has a volume 2R rather than R because of the antipodal identification. So another strange feature is that take this time slice and let them time evolve for a period L/2, then this red line comes to this dashed line. And after doing so, because we already have red line, which is basically time slice for t equals 0, you need to take a trace. But when you take a trace, as you can see, the orientation of the arrows, orientations of the arrows are flipped, which means that when you take a trace, you also need to insert a parity operator. So in summary, this loop channel expansion is given by a trace over the Hilbert space of size 2R, and operator for which we take a trace is a product of parity operator times time evolution operator. And if I decompose this expression into the parity and energy eigenstates, then I get this expression where this epsilon is basically just the parity eigenvalue, and this is just the energy eigenvalue for the states defined on 2R. And so far, everything I said can be applied to any massive quantum field theory. However, in integrable field series, we know that the states are labeled by rapidity of particles, and we know how the parity operator acts on the set of rapidities. And if we carefully check how the parity operator acts on these states labeled by rapidities of particle, then you can conclude that the effect of this insertion of parity boils down to restricting the sum over states to a parity invariant solutions to the beta equation. So normally, if I don't insert any parity operator, you basically need to sum over all possible solutions to the beta equations because they correspond to energy eigenstates. But because of the parity, we need to restrict the sum to the parity invariant solution to the beta equation. And by equating the loop expansion to the tree expansion, we then get this expression. So we first take sum over parity invariant eigenstates of the beta equation, and then take the limit r going to infinity, and that will allow us to read off this prefactor, which is basically the cross-cap overlap. And important point is that this sum over beta equation in the limit r going to infinity, which is the spatial volume going to infinity, could be dealt with the usual thermodynamic beta ansatz if there was no parity constraint. However, here we have a parity constraint, and because of that, we need to think a little bit more. So let me explain you briefly how to deal with the parity constraint. So in order to understand how to deal with the parity constraint, let me just write down the beta equations for parity invariant states. And we need to distinguish two cases, one which has zero momentum rapidity, and the other which doesn't have zero momentum rapidity. So if you don't have any zero momentum rapidity, then the beta equation takes this form. And here we have Pj and minus Pj because the set of rapidities are parity invariant. So if you have the rapidity Pj, then you also have a rapidity minus Pj, and this particle needs to scatter with this particle. And the same applies to this factor as well. And in the case of when there exists a zero momentum rapidity, in addition, we also need to include this factor, which is basically the scattering phase between the particle with momentum Pj and the particle with zero momentum. And now comes the crucial observation. So the crucial observation is that these equations are formally identical to the beta equation with like open bound with boundary conditions. So this is the beta equation for open spin chain or open integrable systems. And in open integrable systems, we have the following beta equations. And here we have the reflection factor, which comes from the the scattering phase coming from the reflecting against the boundary. And if you compare this expression and these two expressions, then you immediately notice that if you replace this reflection phase with SP minus P, you recover this equation. Whereas if you replace RP squared with this SP minus P times SP0, then you recover this T equation. And this basically means that we can recycle the result for the boundary problem if we appropriately replace this factor with some S matrix. So now we want to take the result for the boundary problem and then apply to the Crosscap problem. And so I need to give a very, very brief review of the boundary problem. So for the boundary problem, we can, one interesting quantity, which is basically the analog of the Crosscap overlap, is what's called a G function, or the boundary entropy, which is the overlap between the boundary state and ground state. And this again can be computed by first considering the cylinder with the two endpoints capped off by the boundary state, and then analyzing it in two different channels. So this is a little bit complicated analysis, but people have done it already. And people found a closed form expression for that, for the diagonal S matrix without bound states. And the result is a little bit complicated, and it consists of two parts. And one part is some exponential factor, which is given by some integration of the Y function. And the other part is some ratio of Fredholm determinants. And although it looks complicated, the important point is that all the ingredients are in principle null here. So this G minus and G plus is a Fredholm determinant whose action is defined in terms of Y function and derivative of the S matrix. And the Y function is defined by the usual TVA equation. And important point here is that all the information about the boundary, the details of the boundary, sit here this theta factor. So this, as you can see, that this is the only place where you see the dependence on R of U, where R of U is a reflection factor. And already here, you see something nice is happening for the case of crosscap states, because if I replace this R of P or R of U with this SP minus P or SP minus P SP0, then you can see that there is certain cancellation between the first term and the last term. And this can be worked out more explicitly. And if you do that, then indeed you get a very simple result. So this is basically the result for the crosscap overlap. So let me explain a little bit about the formula. So as I said, the crosscap, if you analyze that wave equation, there are two sectors, one of which I called like S sector and the other I called T sector. So this one basically comes from S sector, and this factor comes from T sector, and both of them are essentially coming from these theta factors. But because theta factor is now simple and also expressible in terms of S matrix, you can get this very simple expression for the crosscap overlap. And this Fredholm determinant is basically the same as what we had before. And so this is the result for the ground state, but you can also extend the result to the excited states by using the famous trick by Dore and Tateo, which involves the analytic continuation. And if you do that, then these Fredholm determinants get modified a little bit. And now, in addition to the integral factor, we also have some discrete sum. And after getting the formula for the excited states, then we can also take the asymptotic limit in which length of the system becomes infinite. And when the length of the system becomes infinite, you can see that this factor just goes away because there is an exponential suppression coming from y function. And all that remains is the contribution from finite sum. And if we do some manipulation, then you can further simplify this finite sum into a finite size determinant, and which is given by this expression. And I should mention that similar formulas showed up in the context of like a defect one-point function in n equals 4 super-mills. But in those cases, there was always some extra prefactor. And so in that context, in that sense, so this crosscap overlap can be viewed as a kind of simplest possible G function. Well, this simplicity is already obvious here, because if you consider G function, which is the overlap between boundary state and the ground state, then there is this complicated prefactor, but now the prefactor is just given by y functions. Okay, so this was basically the result for the crosscap overlap, and you can also check it against some explicit model. And for checking the result, we analyzed what's called staircase model, which was first proposed by Zamolodchikov. So we actually don't know the Lagrangian description of this model, but the remarkable feature of this model, so we only know the S matrix of this model, but the remarkable feature of this model is that if you compute the ground state energy of this model using thermodynamic Bethe ansatz and take this free parameter theta 0 to be sufficiently large, then the ground state energy as a function of the length of the system exhibits infinitely many plateaus. And if you compute the value of the energy of each individual plateau, then it actually matches exactly with the central charges of the unitary minimal models. So for example, this is the Ising model, and this is the critical Ising model. And so this basically means that this model actually like interpolates between infinitely many unitary minimal models. And we basically took this model and computed the crosscap overlap for the ground state. And again, we found that the result exhibits infinitely many plateaus. And we computed the values at plateau analytically and also numerically, and found that the values at plateau agree precisely with the A-series, the result for the A-series minimal models. which you can compute by using conformal field theory techniques. So this is a kind of like one nice verification of our formula. Okay, so any questions so far?
Hi, Shota. I just have a simple question. In case of boundary states, one had to take special care of rapidities at zero, like by some kind of regularization. Do you have any issues with those rapidities here?
Yes, that's very important here. Actually, yes. So this is related to this delta function factor, I think. So this prefactor. So the reason why we have a delta function here in the case of boundary problem is that if you solve the beta equation, sometimes zero rapidity is allowed as mathematically as a solution. But if you really want to construct the wave function, then you discover that the wave function is zero. So basically, u equals 0 corresponds to fake solution to the beta equation. And therefore, when you really compute some physical quantity, you need to subtract the contribution from this fake solution. And that is why we have this extra factor coming from when you compute a boundary problem. And the same applies here as well. However, like if you carefully analyze the problem, you discover that for the S sector, there is no problem of the fake solution, whereas T sector, we do have the problem of the fake solution. And so for S, we just we can just ignore this delta function and replace R with SP minus P. Then you discover that theta factor just vanishes. And that is the reason why this prefactor is just 1 without any extra complication. However, for the T sector, this does contribute, and this is important for getting this simple ratio of Y functions. Okay, so let's proceed. So now we are going to talk. I'm going to talk about integrable spin chains. So again, I'm going to remind you about boundaries in integrable spin chains before I discuss crosscaps in integrable spin chains. So there are two contexts in which people discuss boundaries in spin chain, and we need to distinguish the two. So the first context in which people discuss the boundaries in spin chain is the open spin chain. This is basically boundaries in space. So in this context, you write Hamiltonian as H equals H bulk plus H boundary, and then ask what kind of H boundary preserves integrability. So this problem was well studied in the integrability community since 80s. So another context in which people discuss the boundary in spin chain is what's called boundary states. So those are not boundaries in space, rather they correspond to boundaries in time. So these are some particular states in closed spin chain, which are basically defined as a tensor product of neighboring two-side states. So you construct some like a entangled pair of neighboring two sides and just take a simple product. And so this state is almost a product state, and because it defined very locally, and much like a boundary state in quantum field theory or conformal field theory. And that is why we call them boundary states. And because of this feature, it is also short range entangled, and that is why this is an ideal initial state for studying time evolution of entanglement, because this state has a very, very low entanglement, and then if you time evolve this state, the entanglement increases. And furthermore, if you carefully choose these coefficients in integrable spin chains, then you can get a simple formula for integrable spin chains, which is basically given by a ratio of determinant times some prefactor. And this simple formula is important for analytically studying the time evolution of entanglement. And so now let's talk about the crosscap state in spin chain. So can we define a crosscap state in spin chain? So the naive guess would be, so I should remind you that the Crosscap state is defined by some antipodal identification of the fields. So the naive guess would be, especially in the case of like a spin half chain, is to take a tensor product like this for two antipodal sides, and then, take an entangled pair of two antipodal sides, and then take a tensor product. So this definition looks very much similar to this definition of the boundary state, but physically it is very different because we are making two sides which are antipodally separated, entangled with each other. And because of this, this state has a very, very long range entanglement. And if you compute the subsystem entanglement, then it increases linearly until the subsystem size hits the half of the system size, and afterwards it decreases linearly. So this is in sharp contrast to the subsystem entanglement of the boundary state, which never exceeds log 2. Sorry, subsystem entanglement of the boundary state, which never exceeds log 2. So here in the middle, I basically just drew a curve which corresponds to typical highly excited state in chaotic spin chain. And in that, and as you can see that this Crosscap state has a somewhat similar feature as a typical highly excited state in chaotic spin chain. In addition, this state has a very nice property that it preserves infinitely many conserved charges, and you can show analytically that this Crosscap state is annihilated by this combination of the transfer matrices. And using this state, we also computed the overlap between the Crosscap state and the beta eigenstate. And we found in our paper numerically without a proof that they admit a very, very simple Gaussian determinant formula, which is basically identical to the formula that we obtained by taking the limit of the integrable field theory. And this formula was later proven by Tamas in this nice paper, which appeared in July. And let me just make two comments. So first of all, this formula coincides with the asymptotic limit of the overlap formula for integrable QFTs. And, and this formula is similar to, but simpler than an overlap formula for the spin chain boundary state, which involves non-universal prefactor. So that is also the reason why I call the Crosscap state as a kind of simplest possible boundary state, although physics is a little bit different. And given that now we have a simple expression for the overlap, a natural question is to analyze quantum quench using the Crosscap state as the initial condition. And maybe this provides you a new tractable initial condition for the quantum quench. So in the remaining before going to that, is there any question about this spin chain part? Okay, so in the remaining 5 minutes, let me just explain the application to n equals 4 super mills. So what we basically found is that this Crosscap overlap in spin chain or integrable field theory in 1+1 dimensions basically compute the compute the 1-point function in n equals 4 super mills on what's called RP4 with charge conjugation. So this is the formula. This is basically the summary of what we found. Crosscap overlaps on the worldsheet is equal to 1-point function in n equals 4 super mills on RP4 with charge conjugation. So let me just explain to you what is RP4. So RP4 in the case of for the conformal field theory can be defined in the following. So RP4 is basically like a 4-dimensional version of the Crosscap in which you identify a point and a point that is related to it by an inversion. So this identification maps the exterior of the unit sphere to the interior of the unit sphere. So after this identification, you can take the fundamental domain to be the interior of this unit sphere. And because of this identification, the full conformal symmetry gets broken. And now the 1-point function of local operator can have a non-trivial expectation value. And this provides you a new conformal data for the conformal field theory on RP4. And furthermore, you can also write down a crossing equation for the CFT on RP4, which basically amounts to either performing OP directly. So you take like you put two operators inside a unit sphere, and either you take direct OP or you take OP with a mirror image. So this gives you two different expansions of the same quantity. And if you equate them, you get a crossing equation. And so far, what I said applies to general four-dimensional conformal field theory. But in N equals 4 super mills, we can also define a hard PPS version of a RP4 geometry by combining this inversion with some Z2 identification of the scalar field. We also need to do something for fermions, but let me not talk about it now. And if you just do this identification, it turns out the setup is non-integrable. And you can actually show it at weak coupling and also at strong coupling. Like you can see that the holographic dual corresponding to this RP4 back reacts at ES5 times S5, and then the final geometry is probably no longer integrable. However, we found that integrability gets restored if we combine it with what's called charge conjugation. So basically, what we need to do is to, instead of doing this identification, we do this identification. So here, I'm using the fact that scalar fields in N equals 4 super mills sits in the adjoint representation of SUN. So we can view it as N times N matrices. And when you do the identification, we also do the transposition of the matrix. And this is related to the charge conjugation because the charge conjugation of SUN maps the generator to minus transpose. Now, if you do this identification and compute a propagator, scalar propagator on RP4, then it consists of two terms. So the one is a direct contraction, and the other is more like a contraction with a mirror image. But the contraction with that mirror image involves the transposition. So instead of usual double line, we have a kind of twisted double line where the indices are flipped. So now, now let's try to compute the one-point function using these propagators. But you immediately notice that this part is irrelevant because this basically corresponds to self-contraction, which exists even for like R4 rather than RP4. So if you define operator appropriately on R4, then the contribution from this propagator just disappears. So the only contribution comes from this second propagator. And then what we need to do is to basically like analyze the diagram which survives the leading large N limit. And quite strangely, the leading diagram that survives in this limit looks like a super non-planar, although we are really taking the large N limit. So it basically, the leading large N answer is given by antipodal contraction of single trace operator. So here I'm considering the single trace operator made out of like 6 scalars, like a trace of 5, 6. And the leading large N answer is given by this kind of contraction. And if you do this contraction using this twisted double line, then you can see that there are like 3 phases. So it scales like n to 3. And this is actually the leading. And you can show that all the other diagrams are subleading. And this naturally makes a connection to the Crosscap overlap because now we are contracting antipodal sides of the speed chain. And then we basically did the analysis at weak coupling. And we also have some conjecture at finite to fifth coupling, in particular when the length of the single trace operator is very large. And the final result, well, it's going to be a little bit complicated, but roughly it's given by this expression. So there is no prefactor, but there is a, and then the remaining part is the square root of superdeterminant of what's called Gaudian matrix. And so this Gaudian matrix G is basically given by some derivatives of logarithm of beta equation. And this superdeterminant is basically come from the same Z2 gradient structure. as the defect one-point function. But as I mentioned, like 10 seconds ago, but we don't have any non-universal prefactors. So this is the conjecture, and this is the conjecture that we are trying to test by explicit one-loop computation now. Okay, so finally, let me just mention that this analysis also suggests a new existence of new class of defects in general higher dimensional CFT. So in embedding coordinates, RP4 corresponds to doing this identification. If you don't know the embedding coordinate, this part might be hard to understand, but this is just like a different way of expressing the RP4 using what's called embedding coordinates, which manifest the conformal symmetry structures. And so essentially, you identify x-1 to x-1, but for the other coordinates, you put minus sign. And once you express it in this way, then you can wonder that whether one can define higher codimension versions of RP4, which I would call orientable defects. For example, I can choose x-1 and also x1 to be plus, to come with plus sign, and whereas x2, 3, 4 come with minus sign. So this, well, field theoretically, this should correspond to some kind of higher codimension version of RP4, but as far as I know, not much has been studied for such defects in conformal field theory. So the questions that I wanted to pose here are, can we define them consistently in any conformal field theory? And if so, what are crossing equations? And in n equals 4 supermills, we expect that there should be half BPS versions of these orientable defects. And if you further combine that with the charge conjugation, they probably lead to cross-cap states on the worldsheet, which preserve integrability. So let me conclude because I'm already over time, unless there is some, well, but before, let me just pause to see if there is any question. Okay, so let me conclude. So the punchline is that the crosscap is integrable, and overlap with excited states can be computed analytically, both in spin chain and quantum field theory. And mathematically, it looks like the simplest possible G function. And I was also saying that it's relevant for n equals 4 supermills on RP4 with charge conjugation. And for future directions, as I said during the talk, it will be interesting to study the quench dynamics. And in particular, because the crosscap state has already a large amount of entanglement, an interesting question is whether this entanglement survives if we do something like measurement. And this is a question like I studied a lot recently in the condensed matter community and in the context of measurement in induced phase transition. And that's work in progress with Joel Caetano and Clays and Miao, though they are condensed matter people. And also it's interesting to generalize it to non-diagonal S matrix theories with bound states. So I didn't emphasize much, but so far the result we got is only for diagonal S matrix without bound states. So it's important to generalize the result to non-diagonal S matrix and theories with bound states. And another thing I wanted to emphasize is that because of the simplest form of the final result, this is the best arena for developing quantum spectral curve approach to correlation functions. And also it will be nice to study more orientable defects in n equals 4 supermills and general CFTs. And maybe there might be something interesting if we study crosscap states for fishnet or a Youngian invariance of some crosscap type Feynman diagrams, which look like non-planar but secretly preserves integrability. Okay, yeah, thank you very much.
Thank you very much. Questions?
So in your construction of the crosscap states, so you entangle the spins in the antipolar points, and that's how you created the crosscap. And that's somewhat reminiscent of the ER, EPR, and things like that. So where you literally create the geometry out of the entanglement. So if you push that further, it seems that you can create even handles, for example, by taking some regions and then with the spins to other spins, or in principle, you can create any geometry in a sense. But do you have a, I mean, that's a wide perspective, but do you have any thoughts on this?
Yes, well, I don't have anything sharp, but yeah, that's a good question. Yeah, certainly. So previously, well, first of all, our result might suggest that there are more integrable states, like states that preserve integrability, which are long-range entangled. And for example, so far, before our work, all the integrable states are basically short-range entangled, like boundary states. But now we have one example in which the entanglement is large. So there might be some like a tensor network-like states, which naturally have a relation to geometry, which preserve integrability. And I think that will be very interesting. Like there might be some, if there is some like a mirror-like state, which preserve integrability.
In that context, like if you consider more general, much more general type of entangling by more general tensor network, etc., then do you expect the integrability to persist, or what's going to be the criteria? I mean, that's one aspect I don't see yet.
Yes, so I think the criterion is to see something like this. So this cross-cap state is annihilated by this combination of the transfer matrix.
Okay.
So if there is some tensor network, some state which is constructed by the tensor network that preserves like infinitely many conserved charges and satisfy this kind of relation, then we can say that is an integrable tensor network states.
Yes, yeah, I agree. So, maybe the question is like, is there a better way to practical criteria as to by just giving a look at the tensor network and or maybe reverse engineer, taking some conditional but space, yeah, transfer matrix. Can you construct tensor network compatible with that?
I see. So one thing I can say is that so actually this overlap has a interesting selection rule. So if you compute this overlap, then you can see that the overlap is non-zero only for parity invariant beta states. And there is an argument that this selection rule is related to this integrability condition.
I see.
So one approach is to just compute the overlap and then see if there is any selection rule.
I see. Okay, thank you.
Okay, I have another question. If I understand the work of Gombo and Ekman correctly, they have several examples of cross-cap states. Some states would have minuses involved. So how does it fit into your description?
Yeah, I think in the super M-mills, and that's what you said. Okay. Yeah, in the case of super M-mills, if we consider this half BPS RP4 with charge conjugation, and we only get this particular cross-cap state we constructed. But I expect if we consider different, what we call orientable defects, which basically come from something like this or some other ones, I would expect well, first of all, in order to make it BPS, we also need to do some identification on the scalar sector. And I guess that leads to more general cross-cap states in spin chain.
Okay. Thank you. And well, I also have a comment. You say that these cross-cap states constitute the best arena for the quantum spectral curve, but it seems to me that you keep exactly what is difficult in the quantum spectral curve, with the super-Godin determinant, which is not expressible in Q functions. So the complexity is probably the same, isn't it?
And that is true, but the reason why I was mentioning this is that in these two works, especially in this work, they basically wrote down the conjecture for this ratio of determinant, but they don't have a concrete they don't have a natural Q function representation for the prefactor. So basically what they did in this paper is to express write down some a product of Q function, integral product of Q function representation for this determinant part. And that's precisely the part which shows up in the cross-cap state. So that's why I wanted to say this is the best arena.
Oh, okay.
Anyway,
I get what you mean. Yeah. Okay. Thank you.
Yeah.
Hello, Shota. I wanted to know if you can consider, so you consider Z2 a kind of orbifolds. Can one imagine considering Zn orbifolds?
Right. So
let's say you entangle every states which are at 120 degrees.
Yes, but in that case, yeah, I think it might work, but I just don't. Yeah, we didn't think much about it, and also like I don't know like what I should write here. So maybe like I should write up times up, plus down times down times down. But there can be other possibilities. I think that's an interesting question, which we didn't explore.
And the other question was, but I think you more or less answered to Charlotte. The orbifold defects, do you expect them to be integrable as well?
Yes, in the context of n equals 4 supermeals, if you make it half BPS and then combine with the charge conjugation.
Okay, thank you very much.
Maybe I can ask. Oh, no.
Do you have a holographic interpretation for this crosscap? You mentioned some issue with the non-integrable one.
Okay, yes. Yeah, so non-integrable ones correspond to some back-reacted geometry, which we actually don't know how to UV complete. So these non-integrable ones, so let's see. So non-integrable ones were studied by Caetano and Rastelli, and they identified the dual geometry, but the dual geometry has a naked singularity, and we don't know how to UV complete it. So this is the analysis at the level of supergravity. However, for the integrable ones, the story is much simpler because it's going to be some probe or one plane. So it's just a probe orientifold in ADS5 to ADS5.
Okay, thanks.
So I think that I was going to ask a related question, I think. So, but maybe so for this non-integrable case, the evidence for it being non-integrable is just that you suspect it will be non-integrable, or there is some computation of some.
So they analyzed the 1-point function at tree level, and they basically didn't find the selection rule I was talking about. That doesn't exclude a possibility of having some more complicated formula, a closed form expression, but certainly like it's much more complicated as compared to like a defect 1-point functions.
And the background they have, it solves the supergravity equations, but has a naked singularity. That.
Yes.
Okay. So could you imagine doing some classical string analysis of computing some string motion and seeing some chaotic behavior to check non-integrability, or?
Maybe, but yeah, maybe that might be possible. Yeah, but the background, yes. Yeah, I think that maybe that might be possible. But another thing please.
In the cases where integrability is there, it's much simpler, I guess, yeah.
Yeah, it's much simpler because it's just ADS5 times ADS5.
With your, okay.
With orientifold, yeah.
There is another context where crosscaps actually appear on string side where you didn't mention. So I guess you discussed Young-Mills for SUN, but you can consider SO or SP. So that the dual picture is ADS5 times RP5. So then you'll have, so yeah, the picture is you have D3 branes plus O3 plane. Then in perturbation theory, you have cross caps on non-oriental surfaces. So then in principle, if you think of spin chain, there should be also similar states appearing.
Yes, thank you for asking the question. So yes, so there are actually like a very nice papers by Charlotte and her collaborators, which basically analyze that question. So studying the n equals 4 supermills with SON gauge group or SPN gauge group. Of course, in the leading large n limit, it behaves like almost the same as n equals 4 supermills. But for example, you can ask what happens if you consider 1/n correction to the dilatation operator. And in that case, well, first of all, in that case, like the studying 1-point functions are not interesting because this SON or SPN n equals 4 supermills preserve the full conformal symmetry. So the 1-point functions are all 0. So you need to ask more sophisticated questions. And an example of that is studying the like a 1/n correction to the dilatation operator. So that was studied by Charlotte and others, and they performed both strong coupling and weak coupling analysis. But they, as far as I remember, they didn't find some nice formula. But basically, our analysis suggests that Crosscap states should preserve integrability. So this is basically telling us that there should be nice structure for those 1/n correction to the dilatation operator. And that's a very interesting arena or like a direction to look at.
Hi, Shota, very nice talk. Did you think about what would happen if the spin chain has some quantum group symmetry?
I don't have much to say, but I would expect a similar Crosscap states should exist. And yes, and I think that's an open question because there have been 2 papers which did more like a rigorous studies of this Crosscap overlap, and one by Gambor and another by Ekman, but both studied a rational spin chain.
But presumably then your formula would have to be Q-deformed, the one with up plus down.
Yeah, that's true. That's probably true. But I don't have anything intelligent to say.
Okay, thanks.
Great. If there are no further questions, let's thank Shota again